Hey everyone, I know the board exams are just around the corner, and this chapter can sometimes feel a little intense. But don't you worry, today we're going to break down chemical reactions and equations together, step by step, and make sure you're feeling confident.
Okay, so let's start with something you see every day. Think about an iron gate, getting that reddish-brown layer of rust, or how the food you eat gives you energy, or even how milk, if you leave it out, goes sour. What's happening in all these cases? Well, the original substance is changing into something totally new, with new properties. And that right there is a chemical reaction in action.
So, here's our game plan for today. First, we'll figure out how to spot a reaction. Then, we'll learn the language chemists use to write them down. After that, we'll tackle the super important skill of balancing equations. Then, we'll cruise through the 5 main types of reactions. And finally, we'll see how all this chemistry shows up in our daily lives. A perfect roadmap for your revision.
All right, section 1. So, how can we be absolutely sure a chemical reaction has actually taken place? I mean, you can't see the tiny atoms moving around, right? But what you can see are the results. There are some very specific clues that we can look for. Here they are, the 4 big clues. First, you might see a change in state. Like a solid wax candle burning and turning into gases. Second, a change in color is a huge giveaway. Third, the evolution of a gas. If you drop a piece of zinc into some acid, you'll immediately see bubbles of hydrogen gas forming. And fourth, a change in temperature. That same experiment with zinc and acid, the container would actually feel warm.
Okay, so seeing reactions is one thing, but as scientists, we need a proper way to write them down and communicate them clearly. So this section is all about learning the language of chemistry, how we take what we see and put it down on paper.
Every single reaction has 2 main parts, and it's super simple, really. The things you start with are called the reactants. Think of them as your ingredients. They always go on the left side. The new stuff that gets made is called the products. They always go on the right side of the arrow. That's it.
Now, writing out magnesium plus oxygen gives magnesium oxide is a bit long, isn't it? So to make things easier and more universal, we use chemical formulas. This gives us what's called a skeletal equation. It's short and sweet. But wait a minute, if you look closely, something's not quite right here. We need to fix a problem.
And this fundamental rule is the reason why that last equation was incomplete. The law of conservation of mass is a big deal in chemistry. It basically says you can't just create or destroy atoms out of thin air during a reaction. Whatever you start with, you have to end with. So the number of atoms of each element on the left side must equal the number on the right side. No exceptions.
This brings us to a really important skill for your exam, balancing the equation. Now, I know it can look a bit intimidating at first, but trust me, it's just a logical puzzle. We're just making sure everything adds up, and we're going to walk through one together right now. Let's try to balance the reaction of iron with steam. Let's look at the scorecard here. On the left side, the reactants, we have 1 iron atom, 2 hydrogen, and 1 oxygen. But on the right side, the products, we have 3 iron atoms, 2 hydrogen, and 4 oxygen atoms. The hydrogens look okay for now, but the iron and oxygen are totally out of balance. Our mission is to make them equal. Okay, let's do this step by step. First rule, imagine there are boxes around each formula. We can't change anything inside the box, like H2O can't become H2O2. We can only put numbers in front. Now, let's start with the oxygen. We have 4 on the right, so we need 4 on the left. Simple, we just put a big 4 in front of H2O. But wait. That messes up our hydrogen count. Now we have 4 times 2, which is 8 hydrogens on the left. No problem. To fix it, we just put a 4 in front of the H2 on the right. Now the hydrogens are balanced again. Last up is iron. We have 3 on the right, so we just need to put a 3 in front of the Fe on the left. And now, let's check. 3 iron on both sides, 8 hydrogen on both sides, 4 oxygen on both sides. Perfect. It's balanced.
And there you have it, our final beautiful balanced equation. And you see those little letters in the brackets, the S for solid and G for gas? Those are just state symbols. They give us a little extra information, telling us that solid iron reacts with gaseous water or steam.
Awesome. So now we know how to write equations and how to balance them. The next step is to see that reactions aren't all just random. They actually follow certain patterns, and we can group them into 5 main types. Learning these types makes everything so much easier to understand and remember.
First up, we have the combination reaction. And the name pretty much gives it away, right? It's when 2 or more things combine to form one single product.
A great example is adding water to quicklime. They combine, and you get slaked lime. And if you've ever seen this, you know it gets really, really hot. Any reaction that releases heat like this is called an exothermic reaction. So what's the opposite of combining? Well, it's breaking down. And that's exactly what a decomposition reaction is. One single compound breaks apart into two or more simpler things. But to break something down, you usually need to put energy in, maybe as heat or light or electricity. Since these reactions absorb energy, we call them endothermic.
This slide makes it super clear, doesn't it? Combination is A plus B coming together to make AB. Decomposition is the exact opposite. One thing, AB, breaking apart to make A and B. One usually gives off energy, and the other always takes energy in. They're perfect mirror images of each other.
All right, our third type is the displacement reaction. Think of this one like a competition. A more reactive or stronger element comes along and kicks out a less reactive element from its compound. In the classic experiment, an iron nail, which is more reactive, pushes the copper out of the blue copper sulfate solution. That's why the blue color fades and the nail gets coated in brown copper.
Number 4 is double displacement. Now, if the last one was one element kicking another out, this one is more like a partner swap. The positive part of the first compound pairs up with the negative part of the second, and vice versa. They just exchange partners. And very often, when this happens, one of the new pairs forms an insoluble solid that sinks to the bottom. We call that a precipitate. And finally, our fifth type, oxidation reduction, or just redox for short. Now listen closely. These two things always happen together. You can't have one without the other. Oxidation is when a substance gains oxygen. Reduction is when a substance loses oxygen. In our example here, the copper oxide loses its oxygen, so it gets reduced. And the hydrogen gains that oxygen to become water, so it gets oxidized. One loses, one gains. They're a team. Now, that word redox might sound very technical and complicated, but I promise you, it's a process you see happening all around you every single day. Let's connect it to the real world. Two massive everyday examples of oxidation are corrosion and rancidity. Corrosion is just the sciencey word for when metals get damaged, like when iron reacts with oxygen and water to form rust. And rancidity? That's what happens when the fats and oils in your food, like in chips or old butter, get oxidized. It's what gives them that awful smell and taste. So, if oxygen is the bad guy that makes our chips go stale, how do we stop it? Well, this leads to a pretty cool question. Chip companies have a very clever solution. Before they seal the bags, they flush them out and fill them with nitrogen gas. Nitrogen is very unreactive, so it pushes all the oxygen out and creates a protective cushion, preventing the oils in the chips from oxidizing. It keeps them crispy and fresh. And with that, we're at the end of our revision. I'll leave you with one final thought. Remember exothermic reactions, the ones that release energy? Well, what's the most important one happening inside every single cell of your body right this very second? It's respiration. The glucose from your food is reacting with the oxygen you breathe to give you energy. Chemistry isn't just in a textbook, it's literally keeping you alive. Remember that. Study well, stay calm, and all the very best for your exams. You've got this.